Part 1. Introduction to the Solar System. The Solar System is a gravitationally bound system of celestial objects that orbit a central star, the Sun. It consists of 8 recognized planets, over 200 known moons, 5 officially designated dwarf planets, countless asteroids and comets, and a wide variety of smaller bodies, such as meteoroids, dust, and gas. These components are distributed across a large region of space, extending well beyond the orbit of Neptune, into areas such as the Kuiper Belt and the theoretical Oort cloud. The Sun contains approximately 99.8% of the total mass of the Solar System. Its gravitational pull is the dominant force controlling the orbits of all other objects. The planets orbit the Sun in elliptical paths, mostly in the same direction and roughly within the same plane, known as the ecliptic. This coplanar and codirectional arrangement is a result of the system's common origin. The Solar System formed around 4.6 billion years ago from the gravitational collapse of a molecular cloud composed of gas and dust. The collapse was likely triggered by external forces such as shock waves from nearby supernova explosions. As the cloud collapsed, it conserved angular momentum and began to rotate. The rotating material flattened into a protoplanetary disk, with most mass concentrated at the center, eventually forming the Sun. The remaining material in the disk began to accrete into planetesimals, which collided and merged over time to form protoplanets. The innermost part of the disk, being hotter and denser, allowed the formation of rocky terrestrial planets, Mercury, Venus, Earth, and Mars. These planets are composed primarily of silicate rocks and metals and have relatively thin atmospheres. Farther from the Sun, where temperatures were lower, lighter gases and ices could condense. This led to the formation of the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune. These planets are much more massive and possess thick atmospheres composed mainly of hydrogen, helium, methane, and ammonia. Between Mars and Jupiter lies the Asteroid Belt, a region populated by rocky remnants of the early solar system that never coalesced into a planet, largely due to Jupiter's strong gravitational influence. Beyond Neptune lies the Kuiper Belt, a circumstellar disk of icy bodies including Pluto, Haumea, Makemake, and many other trans-Neptunian objects. Still farther is the hypothesized Oort cloud, believed to contain a vast number of icy bodies and to be the source of long-period comets. However, the Oort cloud has not yet been directly observed. The planets vary significantly in terms of mass, volume, density, surface conditions, atmospheric composition, magnetic fields, and internal structures. Mercury, the smallest planet, has no atmosphere to speak of, while Jupiter, the largest, has a massive atmosphere with complex weather systems and a strong magnetic field. Earth's atmosphere supports life and maintains a stable surface temperature through a balance of greenhouse gases, while Venus's thick carbon dioxide atmosphere results in extreme surface temperatures due to an intense greenhouse effect. Natural satellites, or moons, are common in the solar system. Earth has one, while Mars has 2 small, irregularly shaped moons. The gas giants have extensive satellite systems. Jupiter and Saturn each have over 80 confirmed moons. Some moons, such as Jupiter's Europa and Saturn's Enceladus, are of particular interest due to subsurface oceans that may offer conditions suitable for microbial life. Others, like Saturn's Titan, have dense atmospheres and surface liquid hydrocarbons, making them unique within the system. In addition to moons, several planets have ring systems, with Saturn's being the most prominent and well-studied. Jupiter, Uranus, and Neptune also possess ring systems, although they are much fainter. These rings are composed of dust, ice particles, and rocky debris, and their formation mechanisms vary depending on planetary and orbital dynamics. Asteroids, primarily located in the asteroid belt, are composed mostly of rock and metal. Some follow orbits that bring them close to Earth, classified as near-Earth objects, NEOs. Comets, which originate mostly from the Kuiper belt and Oort cloud, contain volatile ices and dust. When they approach the Sun, solar radiation causes sublimation of their ices, producing a visible coma and tail. The gravitational interactions among solar system bodies can result in orbital resonances, tidal forces, and other complex dynamics. For example, Pluto and Neptune are in a 2 to 3 orbital resonance, meaning Pluto completes 2 orbits for every 3 of Neptune's. Similarly, the Galilean moons of Jupiter exhibit Laplace resonance. Io, Europa, and Ganymede have orbital periods in a 1:2:4 ratio, influencing their internal heating and geological activity. The solar system is not static. Planetary orbits are subject to gradual changes due to gravitational perturbations, particularly from the giant planets. Over long timescales, objects can migrate inward or outward, become captured as satellites, or be ejected entirely. There is evidence that in the early history of the solar system, planetary migration played a major role in shaping the current configuration of planets and minor bodies. This includes the NICE model, which suggests that the outward migration of Neptune disrupted the Kuiper belt and scattered objects throughout the system. The solar system is constantly bombarded by micrometeoroids and influenced by solar radiation and solar wind. Solar activity follows an approximately 11-year cycle, affecting solar wind intensity and the frequency of phenomena such as solar flares and coronal mass ejections. These in turn influence planetary magnetospheres and can impact satellites and power grids on Earth. Exploration of the solar system began in the mid-20th century with the launch of unmanned probes. Notable missions include the Pioneer and Voyager spacecraft, which provided the first close-up data of the outer planets and continued to send information from the edge of the solar system. Galileo, Cassini, and Juno provided in-depth studies of Jupiter and Saturn. Mars has been extensively studied by orbiters, landers, and rovers, such as Spirit, Opportunity, Curiosity, and Perseverance. Recent missions have expanded the frontiers of solar system science. New Horizons conducted a flyby of Pluto in 2015 and is now studying objects in the Kuiper belt. OSIRIS-REx has returned samples from the asteroid Bennu. Upcoming missions aim to explore the icy moons of Jupiter and Saturn, return Martian soil samples, and further investigate the Sun and its interactions with the interplanetary medium. Earth-based observations using telescopes, along with data from space telescopes like Hubble and James Webb, have enhanced our understanding of the solar system's structure, composition, and dynamics. These efforts continue to refine our models of planetary formation, atmospheric evolution, and orbital mechanics. In summary, the solar system is a diverse and dynamic system shaped by gravity, thermodynamics, and time. Its study provides insights into planetary processes, solar interactions, and the potential for life beyond Earth. Ongoing exploration and observation continue to uncover new details about its components and history. Part 2. The Sun, our central star. The Sun is a medium-sized, main-sequence star located at the center of the solar system. It contains more than 99.8% of the system's total mass and provides the energy that drives most processes on Earth and throughout the solar system. It is classified as a G-type main-sequence star, or G2V, meaning it is a yellow dwarf. Although it appears large and dominant in our sky, the Sun is not unusually large or massive compared to other stars in the galaxy. However, its proximity to Earth, approximately 150 million kilometers, makes it by far the most influential celestial object in our environment. The Sun formed approximately 4.6 billion years ago from the gravitational collapse of part of a giant molecular cloud. As the gas and dust condensed, most of the material concentrated in the center, forming a protostar. When the core temperature reached around 10 million degrees Celsius, hydrogen fusion began. This process marked the Sun's entry into the main sequence phase, which it has maintained ever since. During this phase, the Sun fuses hydrogen atoms into helium in its core through the proton-proton chain reaction, a process that converts mass into energy according to Einstein's equation E equals mc squared. The Sun's internal structure is divided into several layers. At the very center is the core, where temperatures reach approximately 15 million degrees Celsius, and where all nuclear fusion occurs. Outside the core lies the radiative zone, a region where energy moves outward primarily in the form of electromagnetic radiation. This process is extremely slow. A photon generated in the core may take hundreds of thousands of years to reach the outer layers. Beyond the radiative zone is the convective zone, where energy is transported by convection. Hot plasma rises, cools, and sinks again, forming convection cells similar to boiling water. Above the interior lies the Sun's visible surface, called the photosphere. The photosphere has an average temperature of about 5,500 degrees Celsius, and is the layer we observe directly through solar telescopes. Sunspots, which appear as dark patches on the photosphere, are cooler regions caused by magnetic activity inhibiting convection. These sunspots often occur in pairs or groups, and vary in number according to the solar cycle. The photosphere is followed by the chromosphere, a thinner and less dense layer that emits reddish light, visible during solar eclipses. Finally, the outermost atmosphere of the Sun is called the corona, an extremely hot and diffuse region extending millions of kilometers into space. The temperature of the corona exceeds 1 million degrees Celsius, a phenomenon that remains an area of active research. The Sun's energy output is measured by its luminosity, which is approximately 3.8 times 10 to the power of 26 watts. Only a small fraction of this energy reaches Earth, but it is sufficient to support life and maintain the planet's climate. The solar constant, which is the amount of solar energy received per square meter at Earth's distance, is about 1,361 watts per square meter. This energy supports photosynthesis, drives weather systems, and warms the surface of the planet. The Sun emits energy across the electromagnetic spectrum, including visible light, ultraviolet radiation, infrared radiation, and smaller amounts of X-rays and radio waves. The ultraviolet portion of this radiation is responsible for both beneficial and harmful effects on Earth. While it helps produce vitamin D in humans, excessive exposure can damage DNA and increase the risk of skin cancer. The Sun's ultraviolet output is also responsible for the ionization of the upper atmosphere, which enables long-distance radio communication. The Sun also emits a constant stream of charged particles known as the solar wind. This wind consists mostly of electrons and protons and flows outward through the solar system at speeds ranging from 300 to 800 kilometers per second. The solar wind interacts with planetary magnetic fields and atmospheres, producing phenomena such as auroras on Earth and other planets. The boundary where the solar wind slows and is no longer able to push against the interstellar medium is called the heliopause, which marks the outer edge of the heliosphere, the region dominated by the Sun's influence. The Sun's magnetic field plays a crucial role in solar activity. It is generated by the movement of charged plasma in the convective zone, producing a magnetic dynamo effect. The magnetic field is not static, but undergoes regular reversals approximately every 11 years, forming the basis of the solar activity cycle. During periods of maximum activity, the Sun exhibits an increased number of sunspots, solar flares, and coronal mass ejections. These phenomena can affect satellites, disrupt power grids, and interfere with radio communications on Earth. Solar flares are sudden and intense bursts of radiation caused by the release of magnetic energy in the Sun's atmosphere. They can emit X-rays and energetic particles that reach Earth in minutes to hours. Coronal mass ejections, or CMEs, are massive bursts of solar plasma and magnetic fields ejected from the corona. When directed toward Earth, CMEs can compress the magnetosphere, cause geomagnetic storms, and generate strong auroral displays. Scientists monitor solar activity using ground-based observatories and space-based missions, such as the Solar Dynamics Observatory and the Parker Solar Probe. The long-term evolution of the Sun is determined by its mass and composition. As a middle-aged main-sequence star, the Sun is approximately halfway through its hydrogen-burning phase. Over the next 5 billion years, it will gradually increase in luminosity and size. Once the hydrogen in its core is exhausted, the Sun will expand into a red giant, engulfing the inner planets and shedding its outer layers. The core will eventually contract into a white dwarf, a dense, Earth-sized remnant composed mostly of carbon and oxygen. This white dwarf will slowly cool and fade over time. Studying the Sun is essential for understanding both our local environment and broader stellar processes. It serves as a natural laboratory for astrophysics, allowing scientists to observe plasma physics, nuclear fusion, and magnetohydrodynamics in real time. The Sun also serves as a benchmark for studying other stars. By comparing its behavior to that of other stars, astronomers can better understand stellar life cycles, planetary system formation, and the habitability of exoplanets. The Sun influences the structure and evolution of the entire solar system. Its gravitational field determines the orbits of planets and smaller bodies, while its radiation affects planetary climates, chemical compositions, and surface processes. On Earth, the balance between solar input and atmospheric conditions determines the climate. Variations in solar output have been linked to climatic events, such as the Little Ice Age. Monitoring the Sun's output is an essential part of climate science, space weather prediction, and satellite protection. Recent missions have aimed to increase our understanding of the Sun's internal dynamics and external effects. The Parker Solar Probe, launched by NASA in 2018, is currently making repeated close passes through the Sun's corona, collecting data on the solar wind and magnetic fields. The European Space Agency's Solar Orbiter mission is observing the Sun's poles and measuring changes in the heliosphere. These missions are providing unprecedented insights into solar processes that are difficult to study from Earth. In addition to modern observations, long-term solar behavior has been reconstructed using historical records and proxies such as tree rings and ice cores. These records reveal cycles of solar minima and maxima that may correspond to changes in Earth's climate. The Maunder minimum, A prolonged period of low solar activity between 1645 and 1715 coincided with a colder than usual climate in parts of the northern hemisphere. Understanding such correlations is important for distinguishing between natural and anthropogenic influences on Earth's climate system. The study of the Sun combines physics, astronomy, climatology, and space science. Its proximity allows for detailed observations, while its central role in the solar system makes it essential to any comprehensive model of planetary environments and interplanetary interactions. The Sun's energy shapes the behavior of the heliosphere, supports life on Earth, and drives atmospheric and geological processes. As our nearest star, it remains a primary focus of scientific research and a critical factor in planning for space travel, satellite operations, and communication infrastructure. Part 3. Mercury, the swift planet. Mercury is the closest planet to the Sun and the smallest of the 8 major planets in the solar system. It has a mean distance from the Sun of about 58 million kilometers, or 0.39 astronomical units. Due to its proximity to the Sun and its short orbital period of approximately 88 Earth days, it was named after the Roman messenger god known for his speed. Despite its closeness to the Sun, Mercury is not the hottest planet in the solar system. That distinction belongs to Venus, due to its dense greenhouse atmosphere. However, Mercury does experience some of the most extreme temperature variations among all the planets. The planet's diameter is approximately 4,880 kilometers, making it slightly larger than Earth's moon. Its surface gravity is about 38% that of Earth's. Mercury has no natural satellites and lacks a substantial atmosphere, meaning that its surface is directly exposed to space. The absence of a significant atmosphere also means there is little to no weather, erosion, or atmospheric shielding from meteoroid impacts. As a result, the surface of Mercury is heavily cratered and resembles that of the Moon. One of the planet's most notable surface features is the Caloris Basin, an impact crater over 1,500 kilometers wide, created by a massive collision early in the planet's history. The force of the impact was so intense that it caused chaotic terrain on the opposite side of the planet due to seismic waves converging through the interior. The surface is also characterized by smooth plains, scarps, and long cliffs, formed as the planet's interior cooled and contracted over billions of years. Mercury's composition is dominated by a large metallic core, which makes up about 85% of the planet's radius. This core is surrounded by a relatively thin silicate mantle and crust. The high metal content suggests that Mercury may have undergone a giant impact in its early history that stripped away much of its original mantle. Despite its small size, Mercury has a magnetic field, approximately 1% as strong as Earth's, which is thought to be generated by a partially liquid outer core. This magnetic field interacts with the solar wind to produce a magnetosphere, though it is small and highly dynamic. One of the most unusual aspects of Mercury is its rotational dynamics. The planet has a 3-to-2 spin-orbit resonance, meaning it rotates 3 times on its axis for every 2 orbits around the Sun. This results in a single solar day, measured from one sunrise to the next, lasting about 176 Earth days. This resonance is caused by the Sun's gravitational influence and the planet's elongated orbit, which has the highest eccentricity of any major planet in the solar system. As a result, Mercury's orbital speed varies significantly, causing unusual patterns in its day-night cycle. Due to the lack of a substantial atmosphere, surface temperatures on Mercury vary dramatically. Daytime temperatures can reach up to 430 degrees Celsius, while nighttime temperatures can plummet to minus 180 degrees Celsius. These fluctuations are the most extreme of any planet in the solar system. The absence of an insulating atmosphere allows heat to rapidly escape during the long nights. Although Mercury has no atmosphere in the traditional sense, it does have an extremely thin exosphere composed of atoms blasted off its surface by the solar wind and micrometeoroid impacts. This exosphere includes elements such as oxygen, sodium, hydrogen, helium, and potassium. Because it is so tenuous, it does not behave like a conventional atmosphere and cannot support weather or protect the surface from radiation. Mercury has been visited by only a few spacecraft. NASA's Mariner 10 was the first to fly by Mercury, conducting 3 flybys between 1974 and 1975. It provided the first close-up images of the planet and revealed its heavily cratered terrain and magnetic field. More recently, NASA's Messenger mission entered orbit around Mercury in 2011 and conducted detailed mapping and compositional analysis until its mission ended in 2015. Messenger confirmed the presence of water ice in permanently shadowed craters near the poles and provided insights into the planet's surface chemistry, interior structure, and magnetic field dynamics. These observations revealed that Mercury's surface contains higher than expected levels of volatile elements such as sulfur and potassium, which challenges earlier assumptions that proximity to the Sun would have depleted such materials. The discovery of polar ice deposits was made through neutron spectroscopy and confirmed by reflectance data showing bright regions consistent with water ice, particularly in craters that never receive direct sunlight. Mercury's orbital and rotational dynamics make it difficult to observe from Earth for extended periods. Because it is so close to the Sun, it is typically visible only during twilight hours, shortly before sunrise or after sunset. Observations from ground-based telescopes are limited by its position low on the horizon and the glare of the Sun. This makes space missions essential for obtaining detailed data about the planet. The European Space Agency and JAXA are currently collaborating on the Bepi-Colombo mission, launched in 2018 and expected to arrive at Mercury in 2025. The mission consists of 2 orbiters, one focused on the planet's magnetosphere and the other on its surface and internal structure. Bepi-Colombo aims to study Mercury's magnetic field, exosphere, and surface composition with far greater precision than any previous mission. It will also test key theories about the planet's formation and its place in the early history of the solar system. Mercury's geological history is thought to include extensive volcanic activity. The smooth plains covering large regions of its surface are believed to be the result of ancient lava flows. However, no active volcanoes have been observed, and most of the volcanic activity likely ceased billions of years ago. Surface features called hollows have also been observed, bright, shallow depressions that may be related to the loss of volatile materials from the surface due to solar heating or space weathering. The high density of Mercury, second only to Earth among the planets, is consistent with its large metallic core. This raises questions about how such a composition formed so close to the Sun. Several hypotheses exist, including one suggesting that early solar radiation may have evaporated the outer layers of smaller protoplanets, or, alternatively, that Mercury was once part of a larger body that lost its outer layers in a massive collision. Mercury provides a unique laboratory for understanding planetary formation, differentiation, and magnetic field generation in small rocky bodies. Its proximity to the Sun, lack of atmosphere, and preservation of ancient surface features offer insights into the early conditions of the inner solar system. Unlike Earth, where plate tectonics and erosion constantly reshape the surface, Mercury has retained its ancient crust, largely unchanged for billions of years. Further study of Mercury will help refine models of solar influence on planetary development and the mechanisms by which small, rocky planets evolve in close proximity to a star. As more data becomes available from upcoming missions and continued analysis, Mercury's role in the overall architecture and evolution of the solar system will become clearer. Part 4. Venus, Earth's twin and fiery neighbor. Venus is the second planet from the Sun, and is often referred to as Earth's twin due to its similar size, mass, and overall composition. Its diameter is approximately 12,104 kilometers, which is about 95% of Earth's. Its mass is roughly 81.5% that of Earth, and it has a comparable surface gravity. However, despite these similarities, Venus differs drastically from Earth in nearly every other respect, particularly in terms of atmospheric conditions, surface temperature, and geological activity. Venus orbits the Sun at an average distance of about 108 million kilometers, or 0.72 astronomical units. It takes approximately 225 Earth days to complete one orbit. One of the most unusual characteristics of Venus is its rotation. The planet rotates on its axis in the opposite direction to most other planets, including Earth, a motion known as retrograde rotation. This means the Sun rises in the west and sets in the east on Venus. Additionally, Venus has an extremely slow rotation rate. A single rotation takes about 243 Earth days, making its day longer than its year. The atmosphere of Venus is composed primarily of carbon dioxide, with trace amounts of nitrogen and other gases. It is extremely dense, with surface pressures about 92 times greater than those on Earth, equivalent to the pressure found nearly 1 kilometer underwater in Earth's oceans. This thick atmosphere contributes to an intense greenhouse effect that traps solar heat, raising surface temperatures to an average of about 465 degrees Celsius. This makes Venus the hottest planet in the solar system, even though it is not the closest to the Sun. The surface of Venus is completely obscured from view and visible light due to a thick layer of clouds composed primarily of sulfuric acid droplets. These clouds reflect most sunlight, giving Venus its bright appearance in the sky. It is often the third brightest object after the Sun and Moon, and is visible shortly before sunrise or after sunset, earning it the titles morning star and evening star. Despite the high reflectivity, the dense atmosphere allows little solar energy to reach the surface, but the greenhouse effect ensures that heat is retained effectively. The planet's surface has been mapped extensively using radar, primarily by the Magellan spacecraft, which orbited Venus from 1990 to 1994. Radar imaging revealed a surface dominated by volcanic plains, mountain ranges, large volcanic domes, and extensive lava flows. Approximately 80% of the surface consists of smooth volcanic plains, with the remaining 20% composed of highlands and elevated terrains. Features such as coronae, large, circular structures thought to be caused by upwelling of magma, are unique to Venus and suggest a history of complex geological activity. Evidence indicates that volcanism has played a major role in shaping the surface of Venus. The planet lacks the kind of plate tectonics found on Earth, but it shows signs of both past and possibly ongoing volcanic activity. Several volcanic features, including shield volcanoes and vast lava plains, suggest widespread eruptions occurred within the last billion years. Some regions exhibit transient thermal anomalies, which may indicate active volcanism, although this has not been definitively confirmed. Venus does not have a global magnetic field comparable to Earth's. This is somewhat surprising given its similar size and likely internal structure, which should support the existence of a liquid iron core. One possibility is that the lack of plate tectonics has limited the cooling of the core, preventing the convective motion needed to sustain a magnetic dynamo. In the absence of a magnetic field, Venus's upper atmosphere is exposed to direct interaction with the solar wind, leading to gradual atmospheric loss via non-thermal escape processes. The upper atmosphere of Venus contains fast-moving winds reaching speeds of up to 360 kilometers per hour, a phenomenon known as superrotation. These winds circulate the planet in only 4 Earth days, far faster than the surface rotation rate. The mechanism behind this superrotation remains an area of active research. The planet also experiences lightning and thunderstorm activity within its dense clouds, similar in some ways to Earth's weather systems but driven by entirely different atmospheric dynamics. Despite its extreme conditions, Venus has been a target of extensive exploration. The Soviet Venera program successfully landed multiple probes on its surface during the 1970s and 1980s. These landers provided the only direct images and data from the surface, confirming high temperatures, crushing pressures, and a desolate rocky landscape. Most of the Venera landers survived for only minutes to a few hours under the harsh surface conditions. Later missions, such as NASA's Magellan and ESA's Venus Express, studied the planet's surface and atmosphere from orbit. The Japanese Akatsuki spacecraft, launched in 2010, is currently orbiting Venus and continues to collect atmospheric data. Venus may have had a more Earth-like climate in its early history, possibly with shallow oceans and moderate temperatures. Models suggest that Venus could have maintained liquid water on its surface for up to 1 to 2 billion years after its formation, depending on the rate of solar evolution and greenhouse feedback. However, a runaway greenhouse effect eventually caused the oceans to evaporate, releasing water vapor, a potent greenhouse gas, into the atmosphere and accelerating the planet's warming. This process may provide valuable insights into the long-term evolution of planetary climates, including potential analogs for climate change on Earth. The absence of water and the high temperatures make Venus extremely inhospitable to life as we know it. However, there has been speculation about the potential for microbial life in the upper atmosphere, where temperatures and pressures are more moderate. In 2020, a controversial claim was made regarding the detection of phosphine gas in the Venusian atmosphere, which some researchers proposed could be a biosignature. However, subsequent analyses questioned the validity and interpretation of the data, and no consensus has been reached. Future missions to Venus are planned to investigate the planet's geology, atmospheric chemistry, and potential habitability in greater detail. NASA's Veritas and Da Vinci Plus missions, along with ESA's Envision orbiter, are expected to launch in the 2030s. These missions aim to study the surface and deep atmosphere with advanced instrumentation, providing higher resolution mapping, atmospheric composition analysis, and possibly sampling the planet's harsh environment using descent probes. Understanding Venus's past climate and geological evolution may also inform our understanding of exoplanets with similar characteristics. Venus remains a key subject in comparative planetology due to its similarities and differences with Earth. Studying why two planets with nearly identical size and composition evolved so differently can improve our models of planetary development and atmospheric behavior. It also contributes to our broader efforts to identify potentially habitable worlds beyond the solar system and to anticipate environmental challenges on our own planet. Part 5. Earth, the life-bearing planet. Earth is the third planet from the Sun and the only known astronomical object to support life. It orbits the Sun at an average distance of approximately 149.6 million kilometers, or 1 astronomical unit. Earth's diameter is about 12,742 kilometers, making it the fifth largest planet in the solar system. It has a mass of approximately 5.97 x 10 to the power of 24 kilograms and a mean density of 5.51 grams per cc, the highest among the planets. Earth is a terrestrial planet with a solid surface, a dynamic atmosphere, and an internal structure that includes a crust, mantle, outer core, and inner core. The Earth's rotation period is roughly 24 hours, and it completes an orbit around the Sun in approximately 365.25 days. The axial tilt of about 23.5 degrees relative to its orbital plane causes the seasonal variations observed throughout the year. This tilt, combined with Earth's revolution around the Sun, results in changing solar insolation patterns, which drive climatic and weather systems. The presence of a relatively large moon helps stabilize Earth's axial tilt, contributing to long-term climate stability. The planet's atmosphere is composed primarily of nitrogen, which accounts for about 78%, and oxygen, which makes up around 21%. The remaining 1% consists of argon, carbon dioxide, neon, helium, methane, and trace gases. Water vapor is also a variable but critical component, especially for weather and climate processes. The atmosphere is structured into layers, including the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. These layers serve different roles in energy transfer, radiation shielding, and atmospheric circulation. Earth's magnetic field, generated by convective motions in its liquid outer core, forms a magnetosphere that protects the planet from charged solar particles and cosmic radiation. This field deflects most of the solar wind and traps some particles in the Van Allen radiation belts. The interaction between the magnetic field and the solar wind can result in auroral phenomena near the polar regions. The field also plays a role in navigation and animal migration, and has been recorded to undergo polarity reversals over geologic time. Approximately 71% of Earth's surface is covered by water, mostly in the form of oceans, with the rest consisting of continents and islands. The oceans regulate global temperature, drive oceanic circulation patterns, and serve as major reservoirs for carbon dioxide and heat. Earth's hydrological cycle involves processes such as evaporation, condensation, precipitation, and runoff, which are critical for maintaining ecosystems and weather systems. The presence of liquid water in stable form is considered a fundamental requirement for life, and Earth remains the only known planet where surface water exists in all three physical states: solid, liquid, and gas. The lithosphere, or Earth's rigid outer shell, is broken into tectonic plates that float atop the semi-fluid asthenosphere. These plates are in constant motion, driven by mantle convection. Plate interactions produce geologic phenomena, such as earthquakes, volcanoes, and mountain building. The movement of plates also results in the recycling of oceanic crust through subduction and the formation of new crust at mid-ocean ridges. Continental drift over millions of years has rearranged Earth's land masses, influencing ocean currents, climate, and the distribution of species. Earth's geological history is divided into eons, eras, periods, and epochs, marking major transitions in climate, biological evolution, and tectonic activity. The planet formed approximately 4.54 billion years ago. The earliest evidence of life appears in rocks that are over 3.5 billion years old. Photosynthetic organisms began to alter the atmosphere by producing oxygen about 2.4 billion years ago, leading to the Great Oxidation Event. This rise in atmospheric oxygen paved the way for more complex life forms. The Cambrian explosion, around 541 million years ago, marked a rapid diversification of multicellular life. Biological evolution on Earth has been influenced by numerous factors, including continental movement, climate change, asteroid impacts, and mass extinction events. The most well-known extinction event occurred about 66 million years ago, when a massive asteroid impact contributed to the extinction of the dinosaurs and led to the rise of mammals. Life on Earth is extremely diverse, ranging from microscopic prokaryotes to complex multicellular organisms. Ecosystems are distributed across terrestrial, marine, and freshwater environments, with biodiversity depending on factors such as latitude, altitude, and climate. The biosphere, the global sum of all ecosystems, is interconnected with the atmosphere, hydrosphere, and geosphere in a complex system that regulates planetary conditions. Key cycles such as the carbon, nitrogen, phosphorus, and sulfur cycles move essential elements through living and non-living systems. Human activities over the past few centuries, particularly the burning of fossil fuels, deforestation, and industrial agriculture, have significantly altered these cycles, contributing to global climate change, ocean acidification, and biodiversity loss. Earth's climate is regulated by a balance of incoming solar radiation and outgoing infrared radiation. Greenhouse gases, including carbon dioxide, methane, and water vapor, trap heat in the atmosphere and maintain a temperature range suitable for life. However, excessive accumulation of greenhouse gases due to anthropogenic emissions has led to an enhanced greenhouse effect, raising global temperatures and altering weather patterns. Climate models project continued warming unless substantial mitigation measures are taken. Earth's moon, with a diameter of about 3,474 kilometers, plays an important role in stabilizing the planet's axial tilt and generating ocean tides. The gravitational interaction between the Earth and Moon causes tidal bulges and contributes to the gradual slowing of Earth's rotation. The Moon is believed to have formed through a giant impact between the early Earth and a Mars-sized body named Theia. Material from the impact coalesced in orbit to form the Moon. Its surface is characterized by impact craters, volcanic plains called maria, and highlands composed of anorthosite. Earth is the most studied planet in the solar system and serves as the baseline for comparative planetology. Observations of Earth from space have revolutionized our understanding of planetary processes, weather systems, and environmental change. Remote sensing, satellite imaging, and global monitoring networks enable the observation of atmospheric composition, land use changes, ocean currents, and ice coverage. This data is critical for managing natural resources, disaster response, and environmental protection. In addition to being home to humans and millions of other species, Earth is the only known planet to have developed a technological civilization. The presence of intelligent life has led to the development of space exploration, which in turn has extended our capacity to observe and study other planets. The study of Earth's climate, geology, and biosphere provides essential context for understanding the potential habitability of other worlds. Ongoing scientific efforts aim to improve models of Earth's systems and to forecast future trends in climate, biodiversity, and geological activity. Research also focuses on identifying biosignatures, indicators of life, that could be used to detect life on exoplanets. Earth remains the reference model against which all other known planets are compared. Understanding its history, structure, and systems is therefore fundamental to the broader field of planetary science. Part 6. The Moon, Earth's Companion. The Moon is Earth's only natural satellite, and the fifth largest satellite in the solar system. It orbits Earth at an average distance of about 384,400 kilometers, and has a diameter of approximately 3,474 kilometers. making it about 1/4 the size of Earth. Its mass is about 1.2% of Earth's mass, and its surface gravity is approximately 1/6 that of Earth. The Moon has no significant atmosphere, no active weather systems, and no liquid water on the surface, although traces of water ice exist in permanently shadowed regions near the poles. The Moon is believed to have formed about 4.5 billion years ago, shortly after Earth itself. The leading theory, known as the giant impact hypothesis, proposes that a Mars-sized body, often referred to as Theia, collided with the early Earth. The impact ejected a significant amount of material into Earth's orbit, which eventually coalesced into the Moon. This theory is supported by similarities in isotopic composition between Earth's mantle and lunar rocks, as well as by computer simulations of planetary collisions in the early solar system. The Moon is tidally locked to Earth, meaning the same side always faces the planet. This occurs because the Moon's rotation period matches its orbital period of about 27.3 Earth days. As a result, the Moon shows a permanent near side and a far side. The near side is marked by dark volcanic plains known as maria, which cover about 16% of the lunar surface and were formed by ancient basaltic lava flows. The far side is heavily cratered and contains relatively few maria. The Moon's surface is covered in a layer of fine, dusty soil called regolith, created by billions of years of meteoroid impacts. This regolith contains small fragments of rock, glass beads, and mineral grains, and it provides valuable information about space weathering processes and the history of the inner solar system. Craters of various sizes are found across the surface, including large impact basins such as the Imbrium, Crisium, and Orientale basins. Temperature variations on the Moon are extreme due to the absence of an atmosphere. Daytime temperatures can reach up to 127 degrees Celsius, while nighttime temperatures can drop below -170 degrees Celsius. The lunar day, from sunrise to sunrise, lasts about 29.5 Earth days. This long day-night cycle contributes to the wide range of surface temperatures and limits thermal equilibrium. The Moon has a differentiated internal structure consisting of a crust, mantle, and core. Seismic data obtained during the Apollo missions suggest a crust thickness of about 30 to 40 kilometers, a partially molten mantle extending to a depth of approximately 1,000 kilometers, and a small metallic core about 350 kilometers in radius. The core is believed to be composed primarily of iron, with smaller amounts of sulfur and nickel. Unlike Earth, the Moon does not currently possess a global magnetic field, but localized remnant magnetism has been detected in some lunar rocks, indicating that a magnetic field existed in the past. One of the most important roles of the Moon is its influence on Earth's tides. The gravitational pull of the Moon causes periodic rises and falls in sea levels, known as tides, which are most pronounced along coastlines. These tidal forces also result in a gradual transfer of angular momentum from Earth to the Moon, causing Earth's rotation to slowly decelerate and the Moon to recede from Earth at a rate of about 3.8 centimeters per year. This long-term interaction is known as tidal evolution and has played a significant role in Earth's geophysical and climatic history. Lunar eclipses occur when Earth passes between the Sun and the Moon, casting a shadow that can fully or partially obscure the Moon. Solar eclipses occur when the Moon passes between Earth and the Sun, casting a shadow on Earth's surface. The apparent size of the Moon in the sky is nearly equal to that of the Sun, which allows for total solar eclipses when the alignment is exact. These phenomena are valuable for studying the Sun's outer atmosphere and for refining orbital models. Scientific exploration of the Moon began with robotic missions in the mid-20th century, followed by the first human landing in 1969 during NASA's Apollo 11 mission. Between 1969 and 1972, 6 Apollo missions successfully landed astronauts on the lunar surface, bringing back 382 kilograms of lunar rocks and soil for analysis. These samples have provided extensive information on the Moon's composition, geological history, and thermal evolution. Remote sensing and geophysical instruments placed on the lunar surface continue to contribute data about lunar interior and seismic activity. In recent decades, lunar exploration has resumed with a new generation of spacecraft. Missions such as NASA's Lunar Reconnaissance Orbiter, India's Chandrayaan series, China's Chang'e program, and other international efforts have mapped the Moon in high resolution, studied its mineralogy, and searched for water ice in shadowed regions. Chang'e 4 became the first mission to successfully land on the far side of the Moon in 2019, and Chang'e 5 returned new lunar samples to Earth in 2020. Water ice has been detected in permanently shadowed craters at the lunar poles, particularly in the South Polar region. These regions receive no direct sunlight and remain at extremely low temperatures, allowing ice to persist over geological timescales. The presence of water ice is of strategic interest for future lunar bases, as it can potentially be used for life support and as a source of hydrogen and oxygen for rocket fuel. Efforts to return humans to the Moon are underway through NASA's Artemis program, which aims to land astronauts near the lunar South Pole. Artemis missions are designed to demonstrate long-duration lunar surface operations and to prepare for future missions to Mars. The development of infrastructure such as the Lunar Gateway, a small space station in lunar orbit, and lunar landers is expected to support sustained exploration and scientific research. The Moon serves as a natural laboratory for studying the early history of the solar system. Unlike Earth, the Moon lacks plate tectonics, weather, and liquid water that would otherwise erode or recycle its surface features. As a result, it preserves a detailed record of ancient impact events and volcanic activity. Studying these processes on the Moon helps scientists understand the timing and frequency of asteroid impacts and the evolution of rocky planetary bodies. The Moon has also become a key reference point for planetary science, astrobiology, and future space settlement. It provides a relatively nearby testing ground for technologies such as habitat construction, in-situ resource utilization, life support systems, and long-duration human presence in space. The low-gravity environment, lack of atmosphere, and surface stability make it a useful site for astronomical observatories and potential radio telescopes shielded from Earth's radio noise. Continued lunar exploration will support scientific discovery, international cooperation, and technological development. Understanding the Moon's origin, structure, and composition is essential for reconstructing the history of the Earth-Moon system and for developing sustainable exploration strategies beyond low Earth orbit. Part 7. Mars, the Red Planet. Mars is the fourth planet from the Sun and the second smallest planet in the solar system, with a diameter of approximately 6,779 kilometers. It is often called the Red Planet due to the presence of iron oxide, or rust, on its surface, which gives it a reddish appearance. Mars orbits the Sun at an average distance of about 228 million kilometers, or 1.52 astronomical units, and takes 687 Earth days to complete one orbit. Its rotational period is approximately 24.6 hours, making a Martian day known as a sol very similar in length to an Earth day. Mars has a thin atmosphere composed mostly of carbon dioxide, accounting for about 95% of the total, with minor amounts of nitrogen, argon, oxygen, and trace gases. The surface pressure is less than 1% of Earth's, and the atmospheric density is too low to support stable liquid water on the surface under present conditions. However, water exists in the form of ice, and seasonal flows of briny liquid water have been suggested in some regions. The atmosphere also contains suspended dust particles that contribute to global dust storms, some of which can envelop the entire planet for weeks at a time. The planet experiences significant temperature fluctuations due to its thin atmosphere and distance from the Sun. Surface temperatures can range from about -140 degrees Celsius at the poles during winter to around 20 degrees Celsius near the equator during the day. At night, the lack of atmospheric insulation causes rapid cooling. These temperature extremes and atmospheric conditions pose challenges for future human exploration. Mars has a surface gravity of about 38% that of Earth and no global magnetic field, although remnant magnetization is present in localized crustal regions. This suggests that Mars once had a magnetic dynamo in its core, which has since ceased. The absence of a protective magnetosphere allows solar wind to interact directly with the upper atmosphere, contributing to the gradual loss of atmospheric particles into space. Measurements from spacecraft, including NASA's MAVEN mission, have helped quantify the current rate of atmospheric escape and reconstruct the planet's climate evolution. Geologically, Mars exhibits a wide range of features formed by volcanic, tectonic, fluvial, and aeolian processes. The planet has some of the largest and most remarkable geological formations in the solar system. Olympus Mons, the tallest known volcano, rises about 22 kilometers above the surrounding plains and spans 600 kilometers in diameter. The Tharsis volcanic region also includes several other massive shield volcanoes. Valles Marineris is an enormous canyon system stretching over 4,000 kilometers in length, up to 200 kilometers in width, and as deep as 7 kilometers in some areas. Evidence of past liquid water is abundant, with features such as dry river valleys, lake beds, delta formations, and mineral deposits that form only in the presence of water. Satellite images and rover data confirm that Mars once had a much thicker atmosphere and sustained stable bodies of liquid water on its surface. Ancient climate models suggest a warmer, wetter environment billions of years ago, possibly supporting habitable conditions. The search for biosignatures focuses on identifying preserved organic molecules and microstructures in sedimentary rocks from that era. Mars has two small, irregularly shaped moons, Phobos and Deimos. They are believed to be captured asteroids from the outer asteroid belt or Kuiper belt. Phobos is gradually spiraling inward due to tidal forces and is expected to either crash into Mars or break apart within the next 30 to 50 million years. The moons have low gravity and are potential targets for future robotic or crewed missions, either as staging points or sources of raw materials. Scientific exploration of Mars has a long history, beginning with flyby missions such as Mariner 4 in 1965. Numerous orbiters, landers, and rovers have since studied the planet in increasing detail. NASA's Viking 1 and 2 missions in the 1970s were the first to land on Mars and conduct experiments in search of life. More recently, missions like Mars Odyssey, Mars Reconnaissance Orbiter, and ESA's Mars Express have mapped the planet's surface and analyzed its mineralogy and climate history from orbit. Surface exploration has been carried out by a series of robotic rovers, including Spirit, Opportunity, Curiosity, and Perseverance. These rovers have studied the geology and chemistry of rocks and soil, searched for signs of ancient microbial life, and collected data on radiation levels, dust, and weather conditions. The Curiosity rover, active since 2012, has analyzed sedimentary rock layers in Gale Crater and identified organic molecules and seasonal variations in methane. Perseverance, which landed in Jezero Crater in 2021, is collecting samples for potential return to Earth and investigating ancient delta deposits that may preserve biosignatures. The Martian polar regions contain large deposits of water ice and carbon dioxide ice, which vary seasonally in volume. The northern polar cap, composed mostly of water ice, remains throughout the year, while the southern cap includes a larger amount of frozen carbon dioxide that sublimates during the summer. These ice deposits are considered essential resources for future human missions, and may also record information about past climate cycles, analogous to ice cores on Earth. Mars is a primary target for planetary protection protocols and astrobiological studies. Its potential for past or even extant microbial life has led to strict sterilization procedures for spacecraft to avoid contamination. Future missions will require similar precautions when returning samples to Earth. The planet's environment offers many of the necessary elements for life: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, but in limited and dispersed quantities. Mars is also central to long-term human exploration goals. Agencies such as NASA, ESA, and private companies, including SpaceX, are planning crewed missions that may begin within the next 2 decades. Key challenges include the duration of interplanetary travel, exposure to cosmic radiation, landing heavy payloads, generating life support systems, and producing fuel and water using in-situ resources. Technologies being developed and tested include closed-loop habitats, autonomous navigation, and precision landing systems. Terraforming Mars, or modifying its climate to make it more Earth-like, has been proposed in theory but remains far beyond current technological capabilities. Ideas include releasing greenhouse gases to warm the atmosphere, constructing orbital mirrors, or importing ammonia-rich asteroids. However, the feasibility, ethics, and environmental consequences of such actions are subjects of debate in both scientific and policy discussions. Mars remains one of the most thoroughly studied and strategically important bodies in the solar system. It represents a key transitional world between the inner rocky planets and the outer gas giants. Its preserved geological record, potential habitability, and accessibility make it a natural focus for research, exploration, and eventual human presence. Ongoing missions and future developments are expected to continue transforming our understanding of the Red Planet. Part 8. The Asteroid Belt. The asteroid belt is a circumstellar disk located between the orbits of Mars and Jupiter, occupying a region of space from approximately 2.1 to 3.3 astronomical units from the Sun. It contains a vast number of irregularly shaped bodies called asteroids or minor planets, which are remnants from the early solar system that never coalesced into a single planet. The total mass of all objects in the asteroid belt is estimated to be about 4% of the Moon's mass, indicating that the belt is relatively sparse despite the large number of objects it contains. The asteroid belt is often imagined as a densely packed region filled with tumbling rocks, but in reality, the objects are separated by vast distances. On average, the spacing between large asteroids is several 100,000 kilometers, making collisions relatively rare. Most asteroids are small, ranging from a few meters to several hundred kilometers in diameter. The 4 largest bodies, Ceres, Vesta, Pallas, and Hygeia, contain more than half of the total mass of the belt. Ceres is the largest object in the asteroid belt, and the only one classified as a dwarf planet. It has a diameter of about 940 kilometers and is composed of a mixture of rock and water ice. Observations from NASA's Dawn mission revealed that Ceres has a differentiated interior with a rocky core and icy mantle, as well as surface features suggesting cryovolcanic activity. Bright spots in the Kuiper crater, composed of salts such as sodium carbonate, indicate the presence of brine and possible subsurface liquid reservoirs. Vesta, the second largest asteroid, has a diameter of about 525 kilometers and is one of the most geologically complex bodies in the belt. Its surface shows signs of ancient lava flows, impact basins, and troughs. The Dawn spacecraft also visited Vesta before traveling to Ceres, providing high-resolution mapping and insights into its basaltic composition. Vesta is thought to be the source of a specific class of meteorites found on Earth, known as HED meteorites. Asteroids in the belt are classified into different spectral types based on their composition and reflectance properties. The three most common types are C-type, carbonaceous, S-type, silicaceous, and M-type, metallic. C-type asteroids are the most numerous and are found primarily in the outer regions of the belt. They are composed of clay and silicate rocks and are dark in appearance. S-types are more reflective and composed mainly of silicate materials and nickel iron. They are more common in the inner belt. M-type asteroids are relatively rare and consist mostly of metallic iron and nickel, possibly representing the remnants of the cores of differentiated planetesimals. The formation of the asteroid belt is linked to the early history of the solar system. During the formation period, planetesimals in this region began to accumulate into larger bodies. However, the strong gravitational influence of nearby Jupiter prevented these objects from forming into a full-sized planet. Instead, collisions and gravitational perturbations led to fragmentation and the formation of a stable belt of debris. Jupiter's orbital resonances, locations where an asteroid's orbital period forms a simple ratio with Jupiter's, created gaps in the distribution of asteroids, known as Kirkwood gaps. These gaps correspond to dynamically unstable regions, where orbital perturbations can cause asteroids to be ejected from the belt or sent into the inner solar system. Some of these ejected asteroids become near-Earth objects, NEOs, and a subset of these pose impact risks to Earth. Studies of asteroid impact probabilities, composition, and orbits are crucial for planetary defense. Projects like NASA's DART mission, which successfully altered the orbit of a moonlet around the asteroid Didymos, are testing techniques for asteroid deflection as a potential mitigation strategy against future threats. The asteroid belt also contains collisional families, groups of asteroids with similar orbital characteristics and compositions that are believed to have originated from the breakup of a common parent body. These families provide valuable information about the internal structure and composition of asteroids, as well as the collisional history of the solar system. By analyzing these families, scientists can reconstruct past events and estimate the age of the belt's components. Exploration of the asteroid belt has been carried out by several spacecraft. In addition to the Dawn mission, other missions have conducted flybys or targeted observations. Galileo flew past Gaspra and Ida on its way to Jupiter, providing the first close-up images of asteroids and discovering Ida's small moon, Dactyl, the first confirmed satellite of an asteroid. Shoemaker orbited and landed on the near-Earth asteroid Eros, collecting detailed data about its surface and internal structure. Asteroids are considered important sources of information about the early solar system. Unlike planets which have undergone significant geological processing, many asteroids have remained largely unchanged since their formation. This makes them valuable time capsules containing pristine material from the solar system's infancy. Meteorites derived from asteroids have been studied extensively in laboratories, yielding information about the age, composition, and thermal history of these ancient bodies. There is growing interest in asteroid mining, both for scientific purposes and potential economic value. Asteroids contain various metals, water ice, and other resources that could support future space exploration missions. Water extracted from asteroids could be used for life support and as a component of rocket fuel, while metals could support in-space manufacturing. Several private companies and space agencies are investigating technologies for surveying, capturing, and processing asteroids. In addition to the main belt, populations of asteroids exist in other regions of the solar system. These include the Trojan asteroids, which share Jupiter's orbit and are located at the L4 and L5 Lagrange points, and the Hilda group, which occupies a 3-2 resonance with Jupiter. Other asteroid groups exist in near-Earth space and within the orbits of Mars and Earth. These populations help scientists understand the dynamic processes that redistribute small bodies throughout the solar system. The asteroid belt remains a region of active research and exploration. Its composition, structure, and dynamics provide critical insights into planetary formation, solar system evolution, and the processes that govern small body interactions. Continued missions, telescopic surveys, and sample return projects are expected to refine our understanding of this ancient and complex region. Part 9. Jupiter, the gas giant king. Jupiter is the fifth planet from the Sun and the largest in the solar system, with a diameter of approximately 139,820 kilometers and a mass more than 318 times that of Earth. It contains over 2.5 times the mass of all the other planets combined. Due to its immense gravity and influence, Jupiter has played a key role in shaping the architecture of the solar system. It is classified as a gas giant, composed predominantly of hydrogen and helium, and lacks a solid surface. Jupiter orbits the Sun at a mean distance of about 778 million kilometers, or 5.2 astronomical units, and completes one orbit approximately every 11.86 Earth years. It has the fastest rotation of any planet, completing a full rotation on its axis in just under 10 hours. This rapid rotation causes a noticeable equatorial bulge and contributes to the formation of its complex weather systems and strong magnetic field. The planet's atmosphere is structured into several bands of clouds that form visible belts and zones. These are driven by high-speed jet streams flowing in alternating directions, producing a striped appearance that is clearly visible from telescopes and spacecraft. The belts and zones exhibit different colors and chemical compositions, primarily consisting of ammonia, water vapor, and trace hydrocarbons. The interaction of rising and sinking gases in these bands leads to the formation of storms and vortices. One of the most well-known features of Jupiter is the Great Red Spot, a persistent anticyclonic storm system larger than Earth. Observed for over 300 years, this high-pressure system rotates counterclockwise and is situated in the southern hemisphere. Its reddish coloration is believed to result from complex chemical reactions involving sulfur or phosphorus-containing compounds, although the exact mechanisms remain uncertain. Beneath the atmosphere, the pressure and temperature increase rapidly with depth. Hydrogen transitions into a metallic state under extreme pressure, forming a layer of metallic hydrogen that conducts electricity and contributes to Jupiter's strong magnetic field. The planet's magnetic field is the strongest of all the planets, roughly 20,000 times stronger than Earth's. It generates intense radiation belts and interacts with the solar wind to form a vast magnetosphere that extends millions of kilometers into space. Jupiter emits more energy than it receives from the Sun due to residual heat from its formation and ongoing contraction. This internal heat source drives convection in the atmosphere and powers much of the weather activity observed on the planet. The core is thought to consist of a dense mixture of elements, possibly including rock and metal, although its exact composition remains a subject of study. Jupiter has a faint ring system, composed mostly of dust particles ejected from its small inner moons due to micrometeoroid impacts. These rings are not easily visible from Earth and were discovered by the Voyager missions. Unlike Saturn's icy rings, Jupiter's rings are dark and composed mainly of small particles of silicate material. Jupiter possesses an extensive system of moons, with over 90 confirmed natural satellites. The four largest moons, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei, who discovered them in 1610. These moons are among the largest in the solar system and display a remarkable diversity of geological features and potential habitability. Io is the most volcanically active body in the solar system, with hundreds of active volcanoes fueled by tidal heating caused by gravitational interactions with Jupiter and the other Galilean moons. Its surface is covered in sulfur and silicate lava flows, and its thin atmosphere is composed mainly of sulfur dioxide. Europa is of great interest to astrobiologists due to its smooth, icy surface and strong evidence of a subsurface ocean beneath its crust. This ocean is kept in a liquid state by tidal heating and may contain more than twice the amount of water found on Earth. Surface features such as linear fractures, chaotic terrain, and plumes suggest ongoing geological activity and the potential for exchange between the ocean and the surface. Ganymede is the largest moon in the solar system, with a diameter of about 5,268 kilometers, larger than the planet Mercury. It possesses a magnetic field of its own, the only moon known to have one, likely generated by a subsurface liquid iron core. Ganymede's surface includes regions of dark, ancient terrain and lighter areas with grooved features, indicating tectonic processes and potential internal heat. Callisto, the outermost of the Galilean moons, has an ancient, heavily cratered surface with little evidence of internal activity. However, measurements suggest it may also harbor a subsurface ocean. Its low radiation environment and geological stability make it a candidate for future human exploration or habitation infrastructure in Jupiter's system. Jupiter has been studied by multiple spacecraft, beginning with flybys by Pioneer 10 and 11, and later Voyager 1 and 2. These missions provided the first close-up images of the planet and its moons. The Galileo orbiter, which operated from 1995 to 2003, conducted detailed studies of Jupiter and its satellite system, including atmospheric entry and analysis of the planet's composition and magnetosphere. More recently, NASA's Juno mission has been orbiting Jupiter since 2016, using polar orbits to study the planet's gravity field, magnetic field, and deep atmospheric structure. The Juno spacecraft has revealed new information about Jupiter's interior, including variations in its gravitational field that suggest differential rotation extending deep into the atmosphere. It has also observed polar cyclones, auroras powered by the planet's strong magnetic field, and the composition of cloud-forming materials such as ammonia and water. Jupiter plays an important role in solar system dynamics. Its large mass allows it to gravitationally influence the orbits of other planets, comets, and asteroids. It has been proposed that Jupiter helped shape the asteroid belt, prevented the formation of another planet in that region, and contributed to the delivery or deflection of cometary bodies that may have influenced Earth's geological and biological evolution. Its gravitational field is capable of capturing interplanetary objects and it occasionally experiences impacts from comets or asteroids, such as the collision of comet Shoemaker-Levy 9 in 1994. Jupiter serves as a model for understanding gas giants and exoplanets with similar characteristics. Observations of exoplanetary systems have revealed many gas giants orbiting other stars, some of which are similar in mass, size, and atmospheric composition to Jupiter. By studying Jupiter's structure, magnetosphere, and satellite system, scientists gain insights into the formation and evolution of planetary systems beyond our own. As exploration of Jupiter continues, both through Juno and future missions like the European Space Agency's JUICE, Jupiter Icy Moons Explorer, attention is focused not only on the planet itself, but also on its potential to harbor life-supporting environments within its moon system. Jupiter remains a central object of study in planetary science due to its immense size, complex atmosphere, dynamic magnetosphere, and diverse satellite system. Part 10. Saturn, the Lord of the Rings. Saturn is the sixth planet from the Sun and the second largest in the solar system after Jupiter. It has a mean diameter of approximately 120,536 kilometers and a mass about 95 times that of Earth. Like Jupiter, it is classified as a gas giant, composed primarily of hydrogen and helium, with a small proportion of heavier elements. Saturn orbits the Sun at an average distance of about 1.43 billion kilometers, or 9.58 astronomical units, and takes approximately 29.5 Earth years to complete one orbit. Its rotational period is about 10.7 hours, resulting in a slightly flattened shape due to its rapid rotation and low average density. Saturn's most distinctive and well-known feature is its complex ring system. Composed predominantly of water ice particles, with some rocky debris and dust, the rings extend from about 7,000 kilometers to over 80,000 kilometers above Saturn's equator. Despite their vast horizontal extent, the rings are extremely thin, often only a few tens of meters thick. The rings are divided into several main components designated as A, B, C, D, E, F, and G rings, each separated by gaps or divisions, such as the prominent Cassini division between the A and B rings. These divisions are caused by gravitational interactions with Saturn's moons and resonances within the ring system. The origin of Saturn's rings remains a subject of scientific investigation. One leading hypothesis is that the rings formed from the remnants of a destroyed moon, or a captured comet that was torn apart by Saturn's tidal forces. Another possibility is that the rings are primordial and have existed since the early formation of the solar system. Observations from the Cassini spacecraft suggest that some parts of the ring system may be relatively young, possibly forming within the last 100 million years, although other components may be older. Saturn's atmosphere is composed of approximately 96% hydrogen and 3% helium, with trace amounts of methane, ammonia, ethane, and other hydrocarbons. The atmosphere is layered into bands of clouds formed at different altitudes by condensation of various chemical compounds. The outermost clouds are composed of ammonia ice, while deeper layers contain ammonium hydrosulfide and water ice. The planet's coloration appears more subdued than Jupiter's due to a lower concentration of colored compounds in its upper atmosphere. Storms and vortices are common features of Saturn's atmosphere. One of the most striking features is the hexagonal wave pattern surrounding the planet's north pole. This persistent, six-sided jet stream has been observed for decades and has no known direct analog elsewhere in the solar system. The storm system includes a central polar vortex and extends deep into the atmosphere. Seasonal changes and variations in sunlight appear to influence the brightness and activity within the hexagon. Like Jupiter, Saturn emits more energy than it receives from the Sun. This excess heat is believed to result from the slow gravitational contraction of the planet and the precipitation of helium droplets within its interior. The helium droplets may fall through the hydrogen-rich outer layers, releasing gravitational potential energy as heat. Saturn's low average density, about 0.69 grams per cc, makes it the only planet in the solar system less dense than water. Saturn has a powerful magnetic field, although it is weaker than Jupiter's. The magnetic axis is closely aligned with the planet's rotational axis, an unusual characteristic among planets. The magnetosphere extends millions of kilometers into space and interacts with the solar wind and Saturn's rings and moons. Charged particles trapped in the magnetosphere produce auroras at the planet's poles, although these are generally fainter than those on Jupiter. The Saturnian system includes an extensive collection of natural satellites, with over 140 confirmed moons. These range from small, irregular objects, only a few kilometers in diameter, to large, spherical bodies with complex geologies. The largest moon, Titan, is larger than the planet Mercury and is the second largest moon in the solar system after Ganymede. Titan has a dense atmosphere composed primarily of nitrogen, with significant amounts of methane and other hydrocarbons. Surface features include lakes, rivers, and seas of liquid methane and ethane, as well as extensive dune fields and evidence of cryovolcanism. Titan is considered one of the most Earth-like bodies in terms of atmospheric pressure and surface liquid processes, though its temperature averages around -179 degrees Celsius. The presence of complex organic molecules and active weather cycles makes it a key target in the search for prebiotic chemistry and potential exotic life forms. The upcoming Dragonfly mission by NASA is scheduled to launch in the 2030s and will deploy a rotorcraft to explore Titan's surface. Another important moon is Enceladus, a small icy body with a diameter of about 500 kilometers. Despite its size, Enceladus exhibits significant geological activity, including cryovolcanic plumes erupting from fractures near its south pole. These plumes contain water vapor, ice particles, salts, and organic compounds, and are believed to originate from a subsurface ocean beneath the ice shell. Data from the Cassini mission provided strong evidence for liquid water, internal heat, and hydrothermal activity, making Enceladus one of the most promising places in the solar system to search for extraterrestrial life. Other notable moons of Saturn include Mimas, known for the large impact crater Herschel that gives it a resemblance to the Death Star, Tethys with extensive ice canyons and fault systems, Dione and Rhea, both heavily cratered and containing possible subsurface oceans, and Iapetus, which exhibits a stark dichotomy between its bright and dark hemispheres. Many of Saturn's smaller moons are located within or near the planet's ring system and interact dynamically with the rings. The Cassini-Huygens mission, a joint project of NASA, ESA, and ASI, provided unprecedented insights into Saturn and its moons. Launched in 1997, Cassini entered Saturn's orbit in 2004 and operated until 2017. It carried the Huygens lander, which successfully descended to the surface of Titan in 2005, providing the first direct observations of the moon's surface and atmosphere. Cassini conducted over 290 orbits of Saturn, multiple flybys of the major moons, and detailed studies of the ring system before intentionally descending into the planet's atmosphere in a planned end-of-mission maneuver. Cassini's discoveries reshaped scientific understanding of Saturn's system, including evidence of seasonal changes, complex atmospheric dynamics, and the potential for habitability on moons like Enceladus and Titan. The mission's data continue to be analyzed, offering insights into planetary rings, satellite evolution, and the dynamics of gas giants. Saturn's role in the solar system is significant due to its gravitational influence, contributions to the population of Trojan and irregular satellites, and interactions with the outer regions of the asteroid belt. Its diverse system of moons and rings provides a natural laboratory for studying planetary formation, resonance dynamics, and the physical properties of ices and volatiles in low-temperature environments. Saturn remains a target for future exploration, with proposed missions focusing on Titan, Enceladus, and the Ring system. Continued study of Saturn will deepen understanding of gas giant evolution, satellite geology, and potential biosignatures beyond Earth. Its unique characteristics and rich system of satellites make it a cornerstone of comparative planetology and outer solar system research. Part 11. Uranus, the tilted ice giant. Uranus is the seventh planet from the Sun and the third largest by diameter in the solar system, with an equatorial diameter of about 51,118 kilometers. It is classified as an ice giant, distinct from the larger gas giants Jupiter and Saturn, due to its higher concentration of water, ammonia, and methane ices in its interior composition. Uranus has a mass approximately 14.5 times that of Earth, and a low density of 1.27 grams per cc, indicating a composition dominated by lighter elements and volatiles. The planet orbits the Sun at an average distance of roughly 2.87 billion kilometers, or 19.2 astronomical units, and takes about 84 Earth years to complete one orbit. Its rotational period is about 17.2 hours. However, Uranus is unique among the planets in that its axis of rotation is tilted by about 98 degrees relative to its orbital plane. This extreme axial tilt causes the planet to rotate nearly on its side, resulting in unusual seasonal variations. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness during its orbital period. The atmosphere of Uranus is composed primarily of hydrogen and helium, with a small fraction of methane, which absorbs red light and gives the planet its characteristic pale blue-green coloration. Compared to Jupiter and Saturn, Uranus has a more uniform and bland appearance in visible light, due to a relatively featureless upper cloud layer. However, deeper imaging using infrared wavelengths has revealed faint banding, storms, and atmospheric structures, especially during periods of increased solar heating near the equinox. The cloud layers are stratified based on temperature and composition. The upper clouds are thought to consist mainly of methane ice, while lower layers may include ammonia and water ices. Uranus has the coldest atmosphere of any planet in the solar system, with temperatures in the upper troposphere dropping to around minus 224 degrees Celsius. The low internal heat output is a distinguishing feature of Uranus, as it emits very little energy beyond what it receives from the Sun, in contrast to most other giant planets that radiate excess heat. Despite the low temperatures and subtle appearance, Uranus has been observed to exhibit dynamic atmospheric behavior. Large storms and dark spots have occasionally been detected, including features similar to Jupiter's Great Red Spot, although on a smaller scale and shorter duration. High-speed winds reaching up to 900 kilometers per hour have also been recorded in the equatorial and polar regions, driven by complex atmospheric circulation patterns. The internal structure of Uranus is believed to consist of three main layers: a small rocky core, a thick icy mantle composed of water, ammonia, and methane, and an outer gaseous envelope of hydrogen and helium. The ice mantle constitutes the bulk of the planet's mass and volume, leading to its classification as an ice giant. Unlike Jupiter and Saturn, where metallic hydrogen is present at high pressures, Uranus likely lacks such a layer due to its smaller mass and cooler interior. Uranus has a magnetic field that is both unusually tilted and significantly offset from the planet's center. The magnetic axis is inclined by about 59 degrees from the rotational axis, and the magnetic center is displaced by approximately 1/3 of the planet's radius. This complex and asymmetric magnetic field results in irregular magnetospheric dynamics and auroral activity. The source of the field is believed to be convective motion within a conducting layer of ionic water-ammonia solution in the interior. The planet has a system of rings, although they are much darker and fainter than Saturn's. Discovered in 1977, the rings of Uranus are composed of narrow, dense bands of icy and rocky particles with high albedo contrast. There are 13 known rings, including the prominent epsilon ring and several other thin and diffuse structures. The rings are maintained by the gravitational influence of small moons known as shepherd satellites, which confine and stabilize ring particles through orbital resonances. Uranus has 27 known moons, named primarily after characters from the works of William Shakespeare and Alexander Pope. The largest moons, Titania, Oberon, Umbriel, Ariel, and Miranda, display a wide variety of geological features, including impact craters, fault systems, ridges, and possible cryovolcanic flows. Ariel appears to be the most geologically active, with evidence of resurfacing events, while Miranda exhibits a complex terrain of cliffs, grooves, and terraced features that suggest a history of significant tectonic activity, possibly due to partial internal melting and reformation. The only spacecraft to visit Uranus was NASA's Voyager 2, which conducted a flyby in January 1986. The encounter provided valuable data on the planet's atmosphere, magnetic field, rings, and moons. Voyager 2 revealed the extreme axial tilt, the offset magnetic field, and the ring system. It also conducted the first close-up imaging of the major moons, revealing previously unknown geological features and atmospheric properties. However, because it was a flyby mission, data collection was limited to a short observation period. Since the Voyager 2 flyby, Uranus has not been revisited by spacecraft, and much of what is known comes from telescopic observations, including those from the Hubble Space Telescope and ground-based observatories using adaptive optics and spectroscopy. These studies have improved measurements of atmospheric composition, seasonal changes, and ring dynamics, but many questions remain about the planet's interior, magnetic processes, and long-term climate behavior. Uranus is a prime target for future exploration, particularly for understanding the nature of ice giants, which are believed to be common among exoplanets in other star systems. A dedicated orbiter mission could study the planet's atmospheric circulation, internal heat budget, magnetic field generation, and moon system in detail. Uranus's moons, especially Ariel and Miranda, are of interest for their geological complexity and potential subsurface oceans. Understanding Uranus is also essential for broader comparative planetology. Its differences from the gas giants in terms of heat emission, axial tilt, and internal structure provide a contrasting model for planetary formation and evolution. The processes that led to Uranus's extreme tilt, possibly a massive collision with a protoplanet early in its history, have implications for understanding angular momentum transfer and orbital dynamics in the early solar system. Uranus remains one of the least explored major planets, with significant gaps in knowledge about its deep atmosphere, magnetosphere, and internal composition. The study of this ice giant will enhance understanding of planetary diversity, both within our solar system and in the context of exoplanetary systems. Part 12. Neptune, the windy blue giant. Neptune is the 8th and farthest known planet from the Sun in the solar system. It orbits the Sun at an average distance of about 4.5 billion kilometers, or 30.1 astronomical units, and completes one orbit approximately every 165 Earth years. With a diameter of about 49,528 kilometers and a mass about 17 times that of Earth, Neptune is slightly smaller than Uranus but more massive, indicating a higher internal density. Like Uranus, it is classified as an ice giant due to the presence of a thick mantle of ices, such as water, ammonia, and methane, beneath its outer atmosphere. The planet's vivid blue color results from the absorption of red light by methane in the upper atmosphere, combined with Rayleigh scattering of shorter blue wavelengths. Although Uranus also contains methane, Neptune's coloration is deeper and more intense, possibly due to unidentified atmospheric components or variations in cloud structure. Neptune's atmosphere is composed mostly of hydrogen and helium, with approximately 1.5 to 2.5% methane. Neptune has a dynamic and active atmosphere, with the fastest winds recorded in the solar system. Wind speeds have been measured at up to 2,100 kilometers per hour, especially in equatorial storm bands and polar jet streams. Despite receiving only about 1/900th of the solar energy Earth receives, Neptune emits more than twice the energy it absorbs from the Sun. This excess internal heat is thought to be the primary driver of its atmospheric circulation. The exact source of this internal heat remains uncertain, but it may involve gravitational contraction, radiogenic heating, or latent heat release from the crystallization of interior materials. Prominent atmospheric features include bands of clouds, storm systems, and transient dark spots. One of the most famous features observed during the Voyager 2 flyby in 1989 was the Great Dark Spot, a massive anticyclonic storm similar in appearance to Jupiter's Great Red Spot. This storm later dissipated and was replaced by others, indicating that Neptune's atmospheric features are transient and evolve over time. Bright high-altitude methane clouds often accompany these storms, casting shadows on the deeper cloud layers. Neptune's interior is structured into 3 main layers: a small rocky core composed of silicates and metals, a thick icy mantle of water, ammonia, and methane, and an outer atmosphere of hydrogen, helium, and methane gas. The transition from the gaseous atmosphere to the icy mantle occurs gradually, as pressure and temperature increase with depth. The icy mantle is a supercritical fluid, a high-pressure state where liquid and gas phases are indistinguishable, containing ionic and conductive materials. This region is believed to be responsible for the generation of Neptune's magnetic field. Neptune's magnetic field is highly tilted, with an inclination of about 47 degrees to the planet's rotational axis and significantly offset from the planetary center. The magnetic field is believed to be generated by convective motions within the electrically conducting portion of the ice mantle. This results in a complex and irregular magnetosphere, with dynamic interactions with the solar wind and charged particle populations. The planet has a system of faint, narrow rings composed of dust and small ice particles. These rings are designated as atoms Leverrier, Lassell, Arago, and Galley, named after astronomers associated with Neptune's discovery and early study. Unlike the more continuous rings of Saturn, Neptune's rings exhibit arc-like concentrations of material. These arcs are maintained by gravitational interactions with nearby moons, particularly Galatea, which acts as a shepherd moon for the Adam's ring. Neptune has 14 confirmed moons, the largest of which is Triton. Triton is unique among major moons in the solar system because it orbits Neptune in a retrograde direction, opposite the planet's rotation. This suggests that Triton was likely captured from the Kuiper belt, possibly after a gravitational interaction that altered its original trajectory. Triton has a diameter of approximately 2,710 kilometers, making it the seventh largest moon in the solar system. Triton is geologically active and exhibits features such as cryovolcanoes, geysers, and a relatively young, sparsely cratered surface. It has a thin atmosphere composed mainly of nitrogen, with trace amounts of methane, and is believed to possess a subsurface ocean beneath its icy crust. Surface features include cantaloupe terrain, ridges, faults, and plains formed by resurfacing processes. Voyager 2 observed plumes erupting from the surface, indicating active cryovolcanism and possible internal heating mechanisms, likely due to tidal flexing following its capture. Neptune's other moons are smaller and more irregular in shape. Proteus is the second largest moon and has a non-spherical form, indicating it is not in hydrostatic equilibrium. Nereid, one of Neptune's outer moons, has a highly elliptical orbit, possibly due to gravitational perturbations caused by Triton's capture. The remaining moons are either inner satellites orbiting close to the planet or outer irregular bodies with distant, inclined, and eccentric orbits. Neptune was discovered in 1846 based on mathematical predictions by Urbain Le Verrier and John Couch Adams, who noticed perturbations in Uranus's orbit that suggested the presence of another planet. Johann Galle confirmed the planet's existence through direct observation using coordinates provided by Le Verrier. This was the first planet discovered through theoretical prediction rather than direct observation. The only spacecraft to visit Neptune was NASA's Voyager 2, which conducted a flyby in August 1989. During its brief encounter, Voyager 2 provided the first and only close-up images of Neptune and its moon Triton. It confirmed the presence of rings, detailed atmospheric features, and magnetic field measurements, as well as detailed observations of several moons. Since then, all studies of Neptune have been conducted via Earth-based and space-based telescopes. Despite its distance, Neptune remains an important subject of planetary science. It serves as a key example of an ice giant, a category of planet that appears to be common in exoplanetary systems. Many exoplanets discovered in the Neptune mass range are located much closer to their parent stars, suggesting a wide diversity in planetary system architectures. Understanding Neptune's formation, migration, and current structure can provide insights into planetary evolution both in our solar system and beyond. Future exploration of Neptune is a major scientific priority, with proposed mission concepts including orbiters, atmospheric probes, and flyby missions. A dedicated Neptune mission could investigate the planet's magnetic field, atmospheric dynamics, ring system, and satellite compositions in detail. Triton, with its retrograde orbit, geological activity, and potential subsurface ocean, is a high-priority target for astrobiological studies. Neptune's distance from the Sun, extreme atmospheric conditions, and unique magnetic field make it one of the most enigmatic and least understood planets. Continued study will enhance understanding of planetary interiors, atmospheric mechanics, and the processes governing outer solar system bodies. Part 13. Dwarf planets and the Kuiper belt. Dwarf planets are celestial bodies that orbit the Sun, are spherical due to their own gravity, and are not moons, but unlike the 8 major planets, they have not cleared their orbital zones of other debris. The category of dwarf planets was formally defined by the International Astronomical Union in 2006, and the best-known example is Pluto. Other recognized dwarf planets include Eris, Haumea, Makemake, and Ceres. The first 4 reside in the Kuiper belt, a distant region of the solar system beyond Neptune filled with icy bodies and remnants from planetary formation. The Kuiper belt extends from about 30 to 50 astronomical units from the Sun and is analogous to the asteroid belt, though it is far larger and more massive. It is populated with small icy bodies, dwarf planets, and comets. Many Kuiper belt objects, KBOs, follow elliptical and inclined orbits, suggesting that the outer solar system experienced significant dynamical disturbances in its early history, possibly involving the migration of the giant planets. Pluto, once classified as the 9th planet, was redefined as a dwarf planet in 2006. It has a diameter of about 2,377 kilometers and an eccentric inclined orbit that takes it from 30 to 49 astronomical units from the Sun. Pluto is composed mainly of rock and ice and has a thin atmosphere primarily made of nitrogen, with traces of methane and carbon monoxide. It exhibits a variety of surface features, including nitrogen ice plains, mountains made of water ice, and possible cryovolcanoes. Pluto has 5 known moons, the largest of which is Charon. With a diameter over half that of Pluto, Charon and Pluto form a binary system, in which both bodies orbit a common center of mass located outside Pluto itself. The other 4 smaller moons, Styx, Nix, Kerberos, and Hydra, follow complex, resonant orbits around the Pluto-Charon system. In 2015, NASA's New Horizons spacecraft conducted a flyby of Pluto, providing the first close-up observations of its surface, atmosphere, and moons. The mission revealed active geological processes, including glacial flows and surface renewal, and detected a layered atmosphere with haze particles. New Horizons continued its journey into the Kuiper belt and performed a flyby of Arrokoth, formerly 2014 MU-69, in 2019, revealing a contact binary object with 2 lobes that likely formed through a gentle collision in the early solar system. Eris, another major dwarf planet in the Kuiper belt, is similar in size to Pluto but slightly more massive. It orbits the Sun at an average distance of about 68 astronomical units and takes around 557 Earth years to complete one orbit. Eris has 1 known moon, Dysnomia, and its discovery in 2005 prompted the re-evaluation of Pluto's planetary status. Eris's surface is highly reflective, indicating a composition dominated by nitrogen and methane ices. Haumea is a fast-spinning, elongated dwarf planet with an estimated diameter of about 2,000 kilometers along its longest axis. Its rapid rotation, about 4 hours, has caused it to take on a flattened, ellipsoidal shape. Haumea is notable for having a ring system, one of the few known ringed objects beyond the giant planets. It also has 2 moons, Hiaka and Namaka. The surface of Haumea is primarily water ice, and its high albedo suggests frequent resurfacing. Makemake is another large Kuiper belt dwarf planet, slightly smaller than Pluto and without a known atmosphere. It has a highly reflective, methane-rich surface and a small moon named MK2. Makemake orbits the Sun at an average distance of about 45.8 astronomical units. Its bright surface and unique spectral characteristics make it one of the more easily observable objects in the Kuiper belt. Ceres is the only dwarf planet located in the asteroid belt between Mars and Jupiter. With a diameter of approximately 940 kilometers, it is the largest object in the asteroid belt and was the first dwarf planet to be visited by a spacecraft. NASA's Dawn mission orbited Ceres from 2015 to 2018, studying its surface, internal structure, and composition. Ceres displays features such as bright salt deposits in craters, possible cryovolcanism, and evidence of subsurface brines. These findings suggest that Ceres may have retained a small amount of internal heat and could have supported transient liquid water in the past. Beyond the Kuiper belt lies the scattered disk, a region with objects in highly elliptical and inclined orbits. Many of these objects, including Eris, are believed to have been scattered outward by gravitational interactions with Neptune. Their orbits are generally unstable over long timescales, and they may serve as a source of some long-period comets. Further still is the hypothetical Oort cloud, a spherical shell of icy bodies thought to surround the solar system at distances ranging from 2,000 to possibly over 100,000 astronomical units. Though never directly observed, the Oort cloud is inferred from the distribution and behavior of long-period comets entering the inner solar system. These objects are thought to be remnants of the primordial solar system, ejected to great distances during the early migration of the giant planets. The study of dwarf planets in the Kuiper belt provides important insights into the formation and evolution of the solar system. These objects are considered to be relatively unchanged since their formation, preserving a record of early solar system conditions. Their varied compositions, orbits, and geologies help refine models of planetary accretion, migration, and collision. Observations of trans-Neptunian objects, TNOs, continue to reveal new bodies with unusual orbital characteristics. Some astronomers have proposed the existence of a large, as yet undetected planet, sometimes referred to as Planet 9, to explain clustering in the orbits of certain distant TNOs. If confirmed, this object would represent a major addition to the solar system's planetary inventory. Ground-based surveys and space telescopes, such as the James Webb Space Telescope, are contributing to the identification and characterization of distant solar system objects. As more TNOs and dwarf planets are discovered, the classification criteria and understanding of planetary systems may continue to evolve. The Kuiper belt and its inhabitants represent the outer frontier of the known solar system. They form a bridge between the planetary region and the vast interstellar space beyond. Studying these distant bodies not only informs models of our own system's history, but also offers context for understanding similar belts observed in exoplanetary systems. Part 14. Comets, Meteoroids, and Meteor Showers. Comets, meteoroids, and meteor showers are all components of the small body population of the solar system. They consist of solid material left over from the formation of planets, and their interactions with the Sun and Earth's atmosphere provide valuable scientific data. These objects vary widely in size, composition, and behavior, but together they offer a record of the solar system's earliest conditions and processes. Comets are icy bodies that originate from two main reservoirs, the Kuiper belt and the Oort cloud. They are composed of volatile ices such as water, carbon dioxide, carbon monoxide, ammonia, and methane, mixed with dust and rocky material. When a comet approaches the Sun, solar radiation heats the ices, causing them to sublimate and release gas and dust into space. This outgassing produces a glowing coma around the nucleus and can generate two types of tails, a dust tail, which curves away from the Sun due to the comet's motion, and an ion tail, which points directly away from the Sun, shaped by the solar wind. Comets are classified into two general types based on their orbital periods. Short-period comets, such as Halley's Comet and Comet Encke, originate in the Kuiper belt and typically complete orbits in less than 200 years. Long-period comets, such as Comet Hale-Bopp or Comet C/2011 L4 Pan-STARRS, are believed to originate in the distant Oort cloud and can take thousands to millions of years to return to the inner solar system. Some comets follow highly eccentric orbits, and many are observed only once before being ejected from the solar system or disintegrating near the Sun. Comet nuclei are typically a few kilometers in diameter and have low albedo due to their dark, carbon-rich surface materials. Despite their small size, the comas and tails of comets can extend for millions of kilometers, making them visible from Earth even when the nucleus is far too small to be resolved by telescopes. The study of comets provides insights into the composition of the early solar system and the delivery of water and organic compounds to Earth and other planets. Several space missions have been conducted to study comets in detail. NASA's Deep Impact mission targeted Comet Tempel 1 by releasing an impactor to excavate material from beneath the comet's surface. ESA's Rosetta mission orbited and landed a probe, Philae, on Comet 67P Churyumov-Gerasimenko in 2014, providing the first direct observations of a cometary nucleus from the surface and detailed data on its structure, outgassing behavior, and composition. Meteoroids are small rocky or metallic objects traveling through space, typically ranging in size from grains of dust to objects several meters in diameter. When a meteoroid enters Earth's atmosphere, it compresses the air in front of it, causing rapid heating that vaporizes the object and produces a visible streak of light called a meteor. If a meteoroid survives its passage through the atmosphere and reaches the ground, the remaining fragment is known as a meteorite. Meteors can vary in brightness and duration. Most are caused by particles no larger than a grain of sand and disintegrate completely in the upper atmosphere. Brighter meteors, often called fireballs or bolides, may be caused by larger meteoroids and can produce sonic booms or fragment into multiple pieces. Meteorites can be classified into three major types: stony, composed of silicate minerals; iron, primarily composed of nickel and iron; and stony iron, a mixture of both. Studying meteorites helps researchers learn about asteroid composition, planetary differentiation, and early solar system processes. Meteor showers occur when Earth passes through a stream of debris left behind by a comet or, in some cases, an asteroid. These showers are predictable annual events, as the debris remains in orbit along the comet's original path. When Earth intersects the stream, particles enter the atmosphere at high speeds, producing numerous meteors. Notable meteor showers include the Perseids in August, associated with Comet Swift-Tuttle, and the Leonids in November, associated with Comet Tempel-Tuttle. Meteor showers are named after the constellation from which the meteors appear to originate, known as the radiant point. While most meteors in a shower are quite small, larger debris can produce fireballs, and the frequency of meteors can range from a few per hour to several hundred during peak activity in particularly active years. The observation of meteor showers contributes to the study of cometary debris trails and their evolution under solar radiation and gravitational perturbations. Occasionally, meteor storms occur when Earth passes through a particularly dense stream of debris, resulting in a dramatic increase in meteor rates, sometimes exceeding thousands of meteors per hour. These events are rare, and often tied to recent disintegration or activity of the parent comet. Historical meteor storms, such as the 1833 Leonids, have had significant cultural and scientific impacts, leading to increased interest in the origin and behavior of meteors. The Tunguska event of 1908 in Siberia is believed to have been caused by the atmospheric explosion of a meteoroid or small comet. It flattened over 2,000 square kilometers of forest but left no impact crater, consistent with an airburst. The Chelyabinsk meteor in 2013, a 20-meter object that exploded over Russia, injured over 1,000 people and highlighted the potential hazards posed by small NEOs, near-Earth objects. These incidents underscore the importance of tracking and characterizing meteoroids that intersect Earth's orbit. Efforts to monitor and catalog NEOs involve both ground-based surveys and space-based infrared observatories. Programs such as NASA's Near-Earth Object Observations Program, the Pan-STARRS telescopes, and ESA's upcoming NEOMIR mission are designed to detect potentially hazardous objects and improve impact risk assessments. Planetary defense strategies include monitoring, impact prediction, and potential deflection techniques, such as kinetic impactors or gravity tractors. Comets and meteoroids serve as critical tools for studying the primordial solar system. Their preserved material, unaltered by geological processes, contains valuable records of the conditions and chemistry of the early solar nebula. Organic molecules found in cometary dust and meteorites provide clues about the origins of life and the delivery of prebiotic material to Earth. Their study bridges planetary science, astrophysics, and astrobiology. Part 15. The Future of Solar System Exploration. The future of solar system exploration is shaped by advances in robotics, propulsion systems, human spaceflight infrastructure, and international collaboration. Scientific goals focus on understanding planetary formation, detecting potential biosignatures, assessing habitability, and preparing for human settlement beyond Earth. Government agencies, private companies, and academic institutions are now playing increasingly interdependent roles in pushing the boundaries of what is technically feasible and scientifically valuable within our planetary neighborhood. One of the most immediate priorities is the continued exploration of the Moon. NASA's Artemis program, supported by international and commercial partners, aims to return astronauts to the lunar surface, establish a sustainable human presence, and develop the Lunar Gateway, a small space station in orbit around the Moon to serve as a staging point for surface missions. Robotic missions from countries including China, India, Japan, Russia, and members of the European Space Agency are also expanding lunar science, with objectives ranging from mapping water ice to sample returns from the far side. Mars remains a high-priority destination for both robotic and crewed missions. NASA's Perseverance rover is currently collecting and caching surface samples for retrieval by a future Mars sample return mission expected to involve a European-built orbiter and NASA's lander and ascent vehicle. These samples will allow for detailed laboratory analysis on Earth and could be key to detecting signs of past microbial life. Plans for human missions to Mars are under development by multiple entities, with projected launch dates in the 2030s or beyond, depending on technology readiness and mission architecture. Key challenges in crewed Mars exploration include long-duration space travel, radiation protection, life support sustainability, psychological and physiological health, surface habitat design, and in-situ resource utilization. Technologies such as Mars surface suits, closed-loop environmental systems, and autonomous robotics are being tested in analog environments on Earth and in low Earth orbit. Proposed surface systems include habitats powered by solar or nuclear energy, systems for extracting water from regolith or ice, and machinery for producing oxygen and methane-based fuel from atmospheric carbon dioxide. Asteroid exploration is growing in both scientific and practical significance. NASA's OSIRIS-REx mission returned samples from asteroid Bennu in 2023, providing critical data on primitive solar material. JAXA's Hayabusa 2 mission returned samples from Ryugu, and future missions will target other bodies including metallic asteroids and binary systems. The scientific goals include understanding the diversity of asteroid composition, thermal evolution, and collisional history. Economically, asteroids offer potential resources such as metals, volatiles, and water ice. which could be used for in-space manufacturing and fuel production. Planetary defense is another important aspect of near-Earth asteroid research. The successful demonstration of NASA's DART mission, which intentionally altered the orbit of Dimorphos by kinetic impact, shows the feasibility of asteroid deflection technologies. Follow-up observations and future missions will test alternative techniques, such as using gravity tractors or surface-altering methods to slowly adjust the trajectory of potentially hazardous objects. Gas giants and their moons remain key targets for advancing planetary science and astrobiology. NASA's Juno mission continues to explore Jupiter's atmosphere, magnetic field, and internal structure. ESA's JUICE mission and NASA's Europa Clipper, both launching in the early 2030s, will investigate the Galilean moons, particularly Europa, Ganymede, and Callisto, which are believed to harbor subsurface oceans. These missions aim to assess habitability, geologic activity, and the potential for life in icy environments. Saturn's system, especially the moons Enceladus and Titan, presents similar astrobiological interest. Proposed missions such as NASA's Dragonfly, a nuclear-powered rotorcraft that will explore Titan's surface, are expected to launch in the late 2030s. Future concepts also include orbiters and landers for Enceladus that could analyze plume material directly for organic compounds and signs of microbial life. Uranus and Neptune are high-priority destinations for the next generation of outer solar system missions. These ice giants remain poorly understood due to limited data from the Voyager 2 flybys. Proposed orbiters would study their atmospheric composition, magnetic fields, internal heat dynamics, and diverse moon systems. Uranus, in particular, has been recommended as a top mission target by planetary science decadal surveys due to its unusual axial tilt, faint ring system, and internal structure. Technological innovation will be central to extending exploration farther into the solar system. Developments in electric and nuclear propulsion systems will allow spacecraft to travel more efficiently to distant targets. Solar electric propulsion, already used in missions like Dawn and BepiColombo, will be further refined. Nuclear thermal propulsion is under consideration for faster crewed missions to Mars, while radioisotope thermoelectric generators, RTGs, and future fission reactors may provide long-lasting power for missions to the outer planets and beyond. In situ resource utilization, ISRU, is crucial for long-term sustainability. Harvesting local materials to produce fuel, water, oxygen, and building components will reduce launch mass and mission costs. ISRU techniques are being developed and tested for use on the Moon, Mars, and asteroids. Additive manufacturing, or 3D printing using local regolith or ice, is another promising approach for creating tools, spare parts, and infrastructure directly on site. Artificial intelligence, machine learning, and autonomous systems will enhance future mission capabilities. AI-driven navigation, hazard avoidance, sample selection, and data analysis will reduce reliance on real-time Earth-based control, especially for distant targets with high communication latency. Swarms of miniaturized spacecraft, including CubeSats and landers, may be deployed together to perform coordinated exploration tasks, enabling more flexible and redundant science collection. Human spaceflight infrastructure in cislunar space and low Earth orbit is also evolving. The International Space Station continues to support microgravity research and human physiology studies. Commercial space stations are being developed to eventually replace the ISS, with modules that support research, tourism, and industry. These platforms will serve as testing grounds for closed-loop life support systems, radiation shielding, and crew behavior studies essential for deep space missions. Global collaboration is expected to increase, with more countries and private entities launching lunar, planetary, and deep space missions. International frameworks for space traffic management, sample return protocols, planetary protection, and resource usage rights will become increasingly important. Treaties and policies must adapt to ensure peaceful and equitable exploration while managing environmental and scientific concerns. Public engagement and education remain key drivers of support for solar system exploration. High-profile missions like Mars rovers, asteroid sample returns, and lunar landings generate public interest, inspire STEM education, and stimulate international cooperation. Outreach efforts by space agencies, universities, and citizen science platforms enable global participation in discovery and data analysis. Over the coming decades, solar system exploration is expected to enter a new phase characterized by simultaneous robotic and human activity across multiple celestial bodies. The integration of advanced science, sustainable engineering, and international policy will shape how humanity explores, utilizes, and understands its planetary neighborhood. The solar system, once accessible only through telescopes and flybys, is becoming an arena of direct presence, sustained exploration, and eventually, human settlement.